in here tomorrow. All right. So on Monday when we talked about limits, we graphed things on the calculator. Ladies, as long as we were approaching the same value from the left or the right, we could say a limit existed at a point. But even if it wasn't the same on both sides, we could say there was possibly a one-sided limit. We could say from the left, it's approaching this. From the right, it's approaching this. Okay. We also talked about the fact that you can say a limit approaches infinity, but that's really not a definition of a limit. Okay, you say it doesn't have a limit, but it is approaching infinity, or increasing without bound, or decreasing without bound, or whatever. Any questions about anything? Anybody worked on the homework on page 743 and had questions? I think I pretty much assigned odds with the exception of 1 or 2 questions, so the answers are in the back to check yourself, okay? Were you here Monday and got the notes, though? Or did I give you the notes? You have it. Okay. Okay. Well, we're going to go on today. I'll try to talk about the graphs as we go, and we're going to do another worksheet tomorrow as well, okay? So I think between today and tomorrow, even if you were gone Monday, you should be fine. There are 2 or 3 limits questions on the final. We're not having a quiz, but we will have a homework check. It says it's due Monday, okay? All right, so yesterday we talked about, or last time we all were here, graphical and using the table, okay, as methods of finding limits. Today we're going to talk about thinking about polynomial functions. We're basically going to talk about end behavior and algebraic ways to find limits. Now, this slide is very basic. It just says if you have a constant function like y equals 6, okay, the limit would be 6. Not real complicated, no matter where you are along the way. If you had like y equals x, the identity function, you would, no matter where you are on the x, the y value would be the same. So that wasn't very exciting. This slide, okay, these are all the properties discussed in this section. Anybody think that looks really fun? Okay. It's not as hard as it looks. The product says, the product property, for example, says the limit as x approaches c of the product of 2 functions is the limit of one function times the limit of the other. But we're not going to work on these. That's the beginning of calculus, and I'm going to, Miss Gupta said it's okay to just let her worry about these properties. We're just going to kind of use a couple select properties today and continue to use graphing and end behavior ideas. All right, so using the properties of limits to evaluate. We looked at a graph, okay, when we did these in 12.1. What I want you to do is, without touching your calculator, what does the graph of that look like, that function, x squared minus 6x plus 3? It's a parabola that opens up. Does it have any holes or asymptotes? No. So at 4, is there something special going on? Well, they want to know what's happening at or near 4. But if we know it's just a continuous graph, we know whatever the x value plugged in will give us the value of y at 4. So if we plug in a 4 here, now see, they use some crazy properties. But when they got down to the end here, they just ended up plugging in a 4. So if we do 4 squared minus 6 times 4 plus 3, we'd have 16 minus 24 is negative 8 plus 3 is negative 5. If we looked at the graph, at 4, the y value is down here at negative 5. All right. So the idea was, if the graph was continuous, it was okay to just substitute in the value. This is going to be called direct substitution. Okay. Notice for the one we just did, the limit, the y value, as x approaches a certain y value, is the value you get when you plug the value into the function. It's just directly substituted it. While this is not true of every function, it is true of polynomial functions and of certain rational functions. Okay, polynomial functions are continuous, right? So you can just plug in and find the limit. It says if you have a polynomial function and c is any real number, then the limit at c is what you get when you plug in c. If you have a rational function, okay, you can do the same thing. You can plug in c as long as you don't get a 0 in the denominator. If it makes a 0 in the denominator, then it's either a whole or an asymptote. That's not news to anybody, I hope. Okay? That means we can't, when you get a denominator of 0, it's undefined, something's going on there, and we can't answer what the limit is at that point without looking into it further. So more simply stated, whoops, I got this on here twice. Anyway, limits of polynomial and rational functions can be found by direct substitution as long as the denominator doesn't equal 0 at that point. These are called well-behaved functions, okay? They're nice little functions. We don't have to spank them or anything, okay? They're very well-behaved. All right, so we're going to look at this first one. This is example off your notes. It says use direct substitution if possible. Do you know something about this, the graph of that? It's degree 4. So it could actually be a parabola, but it might have some loop-de-loops going on in there, but it is going down. Okay, in a minute we're going to talk about end behavior. When you looked at that, did you read every term to yourself, or did you only look at the one of highest degree to decide what it was going to do? Yeah, I only looked and went, okay, the only one that I care about is the negative 2x to the 4th, right? Okay, that's going to be very true when we look at end behavior. The rest of it isn't going to matter. Now, they want to know what's happening at negative 2. Does this have any hole or asymptote or a break in the graph at negative 2? Nope. So we can just substitute negative 2 in, and we have the answer. All right, so if I put in negative 2 in all those places, can anybody figure out what that is? I'm just kind of randomly going through this. I don't know. Is it negative 43? Did anybody type it on their calculator? I'm going to go with that's right. We'll fake it. All right. The first question here is that one we can definitely do by direct substitution because it's just a polynomial. Right? There's no rational function or craziness going on. So we plug in a 3. And we get 2 times 3 squared minus 15, which is what? Okay. So the limit as x approaches 3 is that y will be at 3. At or very near 3. That's it. Okay, think we can handle this? All right. Do you know how to picture that graph in your head? Gotta say, not so much. A square root graph generally does something like this, but this has a cubic inside. A cubic graph does this when it's by itself. A cube root graph does this, but this is not any one of those things, right? Here's my question. We're not sure if anything crazy is going on, but if I put in a 5, can I solve that? I get 5 cubed is 125 minus 4 is 121. Square root of 121 is 11. So it seems like it's defined at that value. Now, I'm going to take a split second here to talk about what we did last time we met. We typed those questions. I'd really appreciate it if people were paying attention. We typed those kind of questions into the calculator on Monday. Square root of x cubed minus 4. We probably started with a zoom 6, which shows this graph does have some undefined values. Okay, so if they had asked us what's happening at -2, we'd have probably had to say does not exist. Okay, can't do it. But this question asks what's happening at 5. So we typed in, trace 5, and it's not going to be in the window, I don't think, but it's at 11. How did we double check that that was okay, that there was a limit there? Do you remember? Hey, Anna, you missed the lesson Monday. Could you pay attention this time, please? What's going on just to the left of 5? Guys, remember we talked about take away a penny? A penny, a 1 cent. At $5, it's at 11. I'm just trying to get you to see what's just to the left of it. Talking about it as a penny helps people see. 4.99. So if I go 4.99 or 4.999, it's really close to 11. Okay? What's the other side? Take $5, add a penny. Where you at? 5.01. So if I check that side, am I also close to 11? Yes. So the limit is 11. Okay? It wasn't doing anything crazy. If you will recall, on Monday we had some graphs where there was some crazy business, where it did this, and then it jumped up here and did this. And then the limit at this point doesn't exist because it's approaching 2 different y values. All right, so that one was just 11. We're also going to have some rational functions like this one down here. Okay, and it's going to say find the limit at 1. If I put a 1 in there, I get 0 over 0. This is called indeterminate form. All right? Division by 0 is undefined, right? So while 0 over 0 seems like that would be okay, it's not. All right? There's something going on there. There could be an asymptote. There could be a hole. We don't know. All right? So what you're going to want to do is, if you can, you're going to take the algebraic expression, factor it, and then see what's going on. This particular one, at 1 had a hole. But again, those of us who were here, we talked about as the x value approached +1 right here, okay, from both sides, what y value was it getting closer and closer to? And this is kind of hard to see. Can anybody see what it's getting closer to? The y value right here is 2. Even though there's a hole there, okay, it's getting closer and closer. The definition of a limit is what is the behavior close to that point doing, not necessarily at that point. All right, so here's one. It asks at -4. If I put a -4 in, is that okay? Can I do direct substitution? No. It's going to give me a 0 in the denominator. Okay? If you factor this, you get x minus 5, x plus 4 over x plus 4. So other than this undefined place, we are left with a line at x minus 5. Now if I substitute in -4, will I get a value? Okay. If you can factor something out and eliminate the undefined place, then you can use direct substitution. All right, so remember we talked about this. We looked at these kind. We said near -4, it was at -9 from the graph. But now we're trying to use some algebraic methods as well. This question on your worksheet is the same. They factored the top. They can divide this factor out. Now they want to know what's happening at 4. You can substitute in the 4 and you get -1. So let's try this one. Is -2 a problem? Sometimes they'll give you a limit that isn't a problem. Even though this has an undefined place, if I asked you to find the limit at 5, you just plug in a 5. Okay? This one asks us to put in a -2 though, and that's a problem, right? So, what can we try? What algebraic method did we just talk about? X plus 7, x plus 2 over x plus 2. So it has a hole at x plus 2, But other than that, the graph just looks like this. It has a hole at -2, sorry. I just didn't word that properly. Other than that, we can now put in a -2 and see what it will be at near that. So if I plug in the -2, what value will this approach? We're good? Positive 5?
Yep.
All right. This graph is not continuous. Where would it be undefined? Yeah, well, at 0. At x equals 0, we'd have a problem, right? But do we have a problem at -4? No. So we just plug in -4, which is -4.25 or -17/4. Is that right? I think so.
Yep.
All right. Number 6.
Are these answers in y equals?
It is the value of y, but you just write equals whatever. Yep. It is a y value. All right. What's going on here? Do I need to do algebra? Why? Right. It's all continuous. It's a polynomial. So we put it at 2, and what do we get? This means the opposite of 2 squared plus 10 minus 1, which would be 5. Number 7 is probably the trickiest one we've come across. We could graph it like we did yesterday. So if this question were on the final exam and you didn't know what to do, graph it. What values would you want to check? 0? Is 0 going to be defined? We know that ahead of time. What else could you check, though? What's really close to 0 on either side? 0.01, 0.001. On the other side? -0.01, -0.001, something like that. All right. I would like to show you, though, algebraically what we can do here. If we expand and simplify this top, what is 3 plus x times 3 plus x minus 9 become? 9 plus 6x plus x squared minus 9 all over. What's the top still simplify down to? 6x plus x squared over x. Now what? Take out an x on the top. Then we can kill the kitty. Not, right? Reduce. And we're at x plus 6. So this is a graph of x plus 6 that has a hole at 0. But can we now use direct substitution? If we put in 0, wasn't that what it was? I can't even remember. It's up the page here. We would get out 6. Do you want me to graph it so you can see that it's near 6? You good? Okay. Now, we are totally shifting gears here. Okay? We're not looking at a particular value for the rest of this lesson, at least this part of the lesson. We're looking at the far left and far right end behaviors. Do you remember the end behavior ideas we discussed before? We talked about if you have a polynomial of even degree, both ends, if it's a positive leading coefficient, both ends are up, yes?
Yep.
Odd degree, positive coefficient, left end down, right end up, negative coefficient, flips it around. Okay? All of those things are the limits at infinity. That's all. We just didn't use that vocabulary before. Okay? It's what's happening at the far left and far right. So this says if you had just a plain old x to the n, so it's just a power, no coefficient besides 1. If it was an even coefficient, it would point up. If it was, I'm sorry, an even exponent would point up. If it was an odd exponent on the left, it would be down, and the right would be up. Okay? Polynomials. Look what this says. It's really complicated to my thinking here, but it says when you have a polynomial function you want to know about out at infinity, it is the limit, and this is saying you only need to look at the highest degree, okay? See what we talked about before, no matter what else this garbage is, you only need to, it's the limit of that highest degree. You don't have to look at all the other stuff. And it says if you're going for negative infinity, it's still the left end behavior of that highest degree. All right? So it says you could use these to evaluate limits of polynomial functions at infinity. Remember, noting that the limit of a function is infinity or negative infinity does not indicate the limit exists, but instead describes, oh, like how that changed color? Instead describes the behavior of the function as increasing or decreasing without bound. When you write the limit as x approaches infinity is infinity, it's really saying the limit doesn't exist, but I know that it's going up, okay? We've already talked about this. It just says if you had a negative coefficient, it flips it around and it makes it approach negative infinity. Anyway, we're going to go on here. Okay. The limit, we talked about this one already. This is the polynomial business, that it refers to the highest power. And this one we talked about a lot when we did, if we're going off to the right, 1 divided by a ginormous number is what? Yes, it's basically 0. Okay? And we talked about if we put a negative infinity in there, it's basically 0, okay? This is a really important property. This is what it looks like. This is on the back side of your worksheet. I don't know, that might have to go back to the other side. Is there one example I skipped? But as you approach infinity or negative infinity, for a reciprocal graph, it's just getting closer and closer to 0, okay? Now, I'm going to make a generalization that's down here as well. It says that's true even if what's in the denominator is a power of x. Okay, if you had over x cubed, that just makes it bigger, right? Infinity cubed just can be a really, 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 really big number. So when you take 1 divided by a huge number, it gets really, really, really tiny and approaches 0. That's a concept we're going to use on a few of these. And again, this only has to do with infinity, okay? This has to do with functions where you're looking for a limit at infinity. All right, this one, I skipped this example, I think. This is a polynomial function, so right here, x to the 5th with a leading coefficient of 1 tells me the shape is this. Well, maybe. Okay, and this asks me what it's doing on the left, and you want to say it's going down, so you write what? The limit is approaching? Okay, and remember that means it doesn't really have a limit, but it is going down. All right. Do you remember when we did rational functions, there was 3 cases for end behavior?
Yep.
If the degree of the numerator was greater, you had to divide it out, and we did synthetic division or long division. Remember that fun?
Yeah.
Okay. If it was degree of the numerator equal to the degree of the denominator, we looked at the leading coefficients. Do you remember that? Yeah. And what happened when the degree of the denominator was greater? Approach 0. Miguel's correct. Okay? This is all we're doing. We're just putting new words to it. Okay? So this, when and only when you have a limit that's approaching infinity, we're going to use this little trick where we divide by the highest power. So this is a rational function, and I want to know what it's doing out at the end. The highest power of x here is x, so I'm going to take each term, 4x over x, that's supposed to be an x, sorry, plus 5 over x, divided by 8x over x minus 3 over x. How does that simplify? this becomes 4, right? Plus 5 over x. Down here, this becomes 8 minus 3 over x. As x approaches infinity, we said both of these things will approach 0, right? 5 divided by some huge number will get close to 0. So what's left? If this approaches 0 and this approaches 0, I'm left with 4/8 or 1/2. Was that just our leading coefficient over leading coefficient business? Okay. Here's another one. This is not the same coefficient or same degree top and bottom, right? But because this is approaching either infinity or negative infinity, they say divide each by the highest power. The highest power of x is what? X cubed. Okay, what's left? 6 over x minus 1 over x squared. 3 plus 1 over x cubed. Okay, if you go back to this property, it says 1 over x, no matter what power is down there, and there's a property of limits that will tell us that it doesn't matter if the top is a 6 either. But this is going to approach 0, this is going to approach 0, this is going to approach 0. So I have 0 minus 0 over 3 plus 0. What is that going to approach? 0. But it's okay. This wasn't okay necessarily because we didn't really know what was going on. And this is okay to say 0 because it's 0 over 3. It's not 0 over 0, right?
Yeah.
Then we have trouble. So it approaches 0. Is that what we learned? Degree of the denominator was greater. It always approached y equals 0. Whoops, did I skip one? Okay. What can we do here? Only because it says infinity. Otherwise, we wouldn't have to do this. But we're going to do that whole dividing thing. And most of you can already tell me the answer. Okay.
Give us a reason to why that works.
Yeah, pretty much. And there's more you have to do with it, I think, in calculus. We get 1 plus 8 over x cubed, and then we get 4 plus 3 over x to the 4th. What's that going to approach? As the denominator here gets huge, this is going to approach 0, this is going to approach 0. Oh, actually, we're going negative infinity. Doesn't matter, those are still going to approach 0, but what are we left with? Would it matter left end or right end? Would it matter if it's positive infinity or negative infinity? It's going to approach the same thing on both ends. All right, help me through these real fast, and they do go fast. What's happening? Okay, it's polynomial, so we only look at this guy. Yep, left end is up, and that's exactly what this is asking. Negative infinity means left. Y values are going up, so we say infinity. What about this one? Yep, 5 divided by infinity squared is going to approach 0. The limit will be 0. Here's one where we'd have to do some dividing by x. Do you know what's going to happen? 6/5, 6/10, or 3/5. Leading coefficient over leading coefficient, right?
Yep.
Okay, what about here? This has a positive leading coefficient. It asks about left behavior, so it is going to be a limit of negative infinity. Is there such a thing as limit of negative infinity? No, means does not exist. It's decreasing without bound. Okay. 12. What's happening here? Anybody know ahead of time? It's going to approach 0. Yep. If I write it out, I get 6 over x plus 2 over x squared, which will both approach 0, divided by 1 plus 1 over x cubed, which is 0. All right. What about this guy? Both ends up, so we're going to say infinity. One half, Miguel said. What do you think? They are equal weight. I'm just writing it out. Okay. More x's in the denominator here, here, and here. So what's left is miracle. All right. This wants to know what the right-hand end behavior is, yes? The limit as x approaches infinity, or t. Suppose the value of a book is equal to this equation after t years, okay? What's going to happen to this little piece right here? Does anybody know? 35 times 0.2 to the t where t approaches infinity. You take 35 and you keep multiplying by 0.2. That's 20%, right? There's only 20% left of it. Then there's 20% of that. Then there's 20% of that. What's that going to approach? 0. Okay? So what's left is going to be 300 over 6. Let's graph it real quick, just so you know I'm not making things up. 300 divided by quantity, somebody help me, 6 plus?
6 plus 3, multiplied by 0.2, and it's the power of x.
Okay, this is the minimum parentheses you need. If x is years, I'm going to go 0 to 20 years for my x. And remember, once you're doing an application problem, if you've chosen an appropriate x window, that is the one and only time when it's okay to choose zoom fit. And it still won't choose the same window I would have chosen, but see what it's doing? Does it appear it's going to have a limit? Looks like it. We could look at our table, but if we trace and we say 10 years from now, what's this book worth? What do you think it's approaching? $50. Okay, which is the 300 over 6, okay, because this approached 0. How much will the book eventually be worth? $50. All right, this is really about what we did Monday. Please, please, please pay attention, because the first and only time today we've discussed one-sided limits. Remember this? That's supposed to be an E, sorry. Why is this a one-sided limit? It wants to know only what's happening as you get closer to 3 from the left, yes? Okay, so as I get close to 3 coming this way, which means this way on the graph, what y value am I really close to right there? To y equals 2. Does everybody see that? Okay. If you weren't here, we did a lot of this. Okay. This one means it's also a one-sided limit. This means as you get close to 3 from the right, so if I'm getting close to 3 from the right, I'm doing this, and it's approaching a clear different y value of 4. So if it had asked this, what would the answer have been? What is the limit at 3? If it's left side is one answer and the right side is another answer, the limit at 3 is said to not exist. This is when you get the limit does not exist. It didn't ask that question, by the way. But it doesn't have one limit because from the left it's doing one thing, from the right it's doing something else. All right. Yay. Okay. We are going to work on this for the 7 minutes that are left. You can work on worksheet 3. Then we're going to have